Task 30 deals with the question on how bifurcations are modeled in the Isaac model, followed by recapping what integrators and resonators are, and lastly how those two then relate to the simple 2D Isaac model. So of course we could start with again explaining what this model exactly is and how it works in detail. However, we were already introduced to the integrate and fire model and the resonate and fire model and so on in several tasks beforehand. For example, task 6 and then again in task 7 or task 18, where it was compared to other models as well. Thus, since we did not want to be repetitive by explaining the whole model again, we will assume that you already have a rough understanding of this concept by looking at the earlier videos. If not, now it's the time to pause the video and open up the old ones again. If you're hearing this now, either you have just finished watching the videos, are brave and/or intelligent enough to continue, or maybe just forget to pause. Either way, let us actually begin with this task. So, bifurcations. There are several types of bifurcations, and if everything worked out, then the group just before us should have explained it to you just now. But how are bifurcations modeled in the Isaac model explicitly? For that, we can take a look at this bifurcation diagram of the quadratic integrate and fire neuron. But wait, what is the quadratic integrate and fire model? We only had the original integrate and fire model till now. But don't worry, it is just a more simplistic version, which due to their universality makes it a bit more easier for us to model large-scale simulations. For that, we just replace -v with +v square in the usual integrate and fire model. And if v reaches v peak, then v is set to v reset, and thus we get the quadratic integrate and fire model. Here, v peak is not a threshold, but the peak of a spike. In simulations, the peak value is assumed to be large but finite, so it can be normalized to 1. Here, b portrays the dynamic behavior, so decides whether the system is resonating or integrating, but we will recap this in the second part of this video. V, on the other hand, stands for the voltage, and by resetting V to V reset, the quadratic integrate and fire model nicely portrays repetition when the saddle node bifurcation is on an invariant circle. So now we can actually take a look at our diagram. But first of all, let us see what different behaviors are depicted in it. We can quantify the properties of a neuron in each of the different orbits. So either the properties of this orbit under the curve, or the properties for the right side here, which are characterized by values for b larger than 0. And lastly, we have principal behavior for this smaller part up here in green, where we have bistability. So with this, if we now use the tools we have based on the type of bifurcation, we can analyze the principal behavior of a system. Now changing these parameters allows us to induce different kind of principal behavior in the system. By changing these parameters, they allow us to go in between areas with different principal solutions, and at the point where the set of possible solutions changes, we have a bifurcation. In that sense, V reset and B are the bifurcation parameters of the system. Depending on the value, the types of bifurcation that happens are different. But let us first go step by step so we can clearly follow each step. So we begin with our empty diagram that we will fill up in the following. As an example, we will start with the parameter b as the bifurcation parameter. Thus we look at the transition from the left to the right side, where we can change the parameter b from smaller than 0 to larger than 0. When b is smaller than 0, b plus v square has two zeros. One corresponds to the stable node equilibrium, the resting state, and the other one corresponds to the unstable node, the threshold state. When b is larger than 1, the right-hand side of the model is strictly positive, and the neuron fires a periodic train of action potentials. Indeed, v increases, reaches the peak, resets to v reset, and then increases again. So the basic thing is that we have here a shift upwards of the curve, and this shift leads to the fact that actually the unstable and stable fixed points that we have seen on the left-hand side approach each other and annihilate each other. So that means increasing B will make the excitable system that would essentially produce a single spike, so it would actually go back. it will shift the system to a system that actually produces periodic firing. So very different kind of behavior, which is characterized by saddle node on invariant circle bifurcation. The next type of transition is similar to the one that we just discussed. So just that we go from an excitable behavior as seen on the bottom left to this area of bistability. To get there, we in this case have to cross this line here, thus our second parameter v reset is of utmost importance here. So instead of transitioning to an invariant circle, we are now transitioning to a saddle homoclinic orbit, which means this system can actually go from here into this orbit, and then it will be a closed orbit where the system will repeat this activity essentially forever. And then we have for now our last transition from here, our bistability area, to here our periodic behavior as seen on the bottom right. And thus we transition into a saddle node bifurcation as seen here. And where all these behaviors meet, we then even have the saddle node homoclinic orbit bifurcation. We can now play this for any of these transitions, and you will see that actually the behavior is now purely described by just these pairwise analysis of the parameter v reset and parameter b. And as you see, given the complexity of the simple equation, we get already an interesting and large number of different kinds of bifurcation. So that allows us to produce a large number of different principal behavior of the neuron as well. And that means this Isaac-Cabbage model can produce very rich dynamic behavior. However, this diagram is only an integrator. Now for the second part of our task. Integrators, resonators and their relation to the simple 2D model. For that we have to quickly define two aspects. The definitions of integrators and resonators, and then moving on to the question of which simple 2D model we are talking about. So first of all, our recap of integrators and resonators. What are their properties and how are they distinct from one another? All excitable systems can be classified by a certain feature: the existence of subthreshold oscillations. When there are no such oscillations, we call it an integrator, while their existence constitutes that the system is a resonator. This division uniquely determines the type of bifurcation, or the other way around, that the bifurcations divide neurons into these categories. For example, neurons near saddle node bifurcation are integrators as the eigenvalues don't have an imaginary part. They prefer high-frequency excitatory input, have well-defined thresholds, and fire all or non-spikes with some latencies. For example, the quadratic integrated phi neuron is a genuine integrator. Neurons near Andronovo-Hopf bifurcation are resonators, which eigenvalues do not have an imaginary part. They have oscillatory potentials, prefer resonant frequency input, and can easily fire post-inhibitory spikes. So in an integrator system, the equilibrium is a node, while it is a focus in the case of the resonator. Now we come to our simple 2D model, what it actually is. The ultimately simple 2D Isaac-Cabbage model is a model where the constants were rescaled to simplify the expression further. So we have only 4 parameters, but still a nonlinear model. The relation of integrators and resonators in a simple 2D model is actually quite on phase. Depending on the value of A and B, the simple 2D Isaac-Cabbage model can act both as an integrator or a resonator, since those parameters both affect the subthreshold dynamics. So if we look at an example of such simple models in a bit more detail, we can see it more clearly. Just for clarification, the U-null clients are the straight lines here, and the V-null clients are the parabola here. In both cases, we have a stable node depicted in black, and on the left, we see an additional saddle node in white. To know that, we have to do our stability analysis, but you already know that. If not, we explained it before in task 11, so if you are watching it on YouTube, you can just switch over to it. Knowing what those are now, you can actually analyze the different behavior and associate the integrator behavior on the left-hand side and associate the resonator behavior on the right-hand side, because we have a focus. And that's it! With this video, we have shown you how bifurcations can be modeled in the Isaac-Cabbage model. We have shortly recapped what integrators and resonators are to see how they relate to our simple 2D Isaac-Cabbage model. And if you want to take your own closer look at the topics that we have presented, here are our references, and we did mainly focus on the contents of the book chapters. And if you have any questions, don't hesitate to ask.